Log on, tune in, find out. Another good idea from Cambridge.
It's a great privilege now to introduce Professor John Page from the University of Alberta in Edmonton. Don Page did his PhD at Caltech on accretion into and emission from black holes, and this was supervised by Kip Thorne and Stephen Hawking. And Don came to Cambridge after that and worked as a postdoctoral assistant in labs with Hawking, and has written quite a number of papers with Stephen Hawking too. So he's been in various places since then, and at the University of Alberta since 1990. He is takes a very big interest in this area of multiverses now, and is a strong proponent, I think I may say, of multiverses. So we're going to have an interesting time with the next couple of lectures as we explore that. So, Don, very warm welcome.
Yes, well, thank you. Thank you very much. It's great to be back in Cambridge, where I was a postdoc and reminiscing old things. I was flying in. I saw Helen out of the airplane that I had the chance to hike up, and then of course seeing here in this morning I got at 5:30, went down along the cam and back out to Grantchester Meadows. I went for a swim in the cam, and anyway, enjoyed being back. I don't know how many of you have climbed this mountain. I found that Don Morton has climbed it. This is Mount Temple in Canada, so the last thing will be from the top. Anyway, so I'm very happy to be here. I guess it's everybody. This today is either working in Cambridge now or had worked in Cambridge, so it's Cambridge Day, I guess. So I want to talk about some issues with multiverse, and particularly in some sense, maybe addressed to fellow theists, my feeling that we shouldn't feel threatened by multiverses, or that we shouldn't necessarily assume that multiverses are wrong. So I want to be open to that. I mean, like Lemaître, I do not wish to say that I am an evangelical Christian, but I don't wish to say that my theology is tied to any particular model of the universe. But I am open to multiverses, and I do feel that they seem to be rather attractive. So I'll try to give some defense of that, but I by no means certain that multiverses are correct. And in any case, I'm not believing in multiverses for theological reason, although conceivably there's some psychological effect that, if I believe in God and spiritual worlds, well, maybe it makes it easier for me to believe of other physical worlds. So maybe there's a psychological connection there, but not anything direct. Okay, now, before Darwin, some Christians took the marvels of humanity as evidence of separate and individual design, that each species was separately designed. However, Darwin has shown that we're related to the rest of the biosphere. It seems that we weren't created entirely separate from that. That, of course, does not prove that. I mean, that does not disprove the idea that God created the whole thing, but it just says maybe the arguments that people have used for separate design don't work. Well, now some Christians take the marvels of the constants of physics as evidence of separate and individual design of those constants, that God fine-tuned the constants. So I'm raising the possibility that this could be equally mistaken, and I'm trying to warn theists and Christians and other theists, perhaps it's a bit dangerous to go along that route, because that particular argument might get undercut in the same way that the Paley-type design arguments were somewhat undercut by Darwinian evolution. Now, it does seem true that we could not be here if many of the constants of physics were significantly different. So, I mean, Martin Rees has talked about 6 constants of the universe. I'm not going to go into any detail of the technical things about this, but if the mass and charge of the proton and the electron were much different, suitable stars to produce elements and to sustain planets could not exist. And the cosmological constant, there has been a lot of discussion about that. If that weren't so tiny, it's 122 orders of magnitude smaller than unity in Planck units, if it weren't nearly that tiny, structures wouldn't form at all. That is, if it were of order unity, it's very hard to see how we can have structures, because everything would be quantum gravity. So it does seem that there are constants that seem to have rather special values for us to be here. Now there's different explanations of this. Some say the fine-tuning was done separately by God to allow life. God chose the constants so that we could be here. Others say it's an accidental fluke and that we can't have any explanation. That's the way they are, no explanation. Yet others say that it arises from a huge multiverse of many different possible constants of physics, that there could be different parts of the universe that have different constants of physics. It's a little confusing, what's a universe and what's a multiverse. In some sense, I tend to think that the entirety of what's described by the laws of physics, and maybe the entirety, if it is quantum, everything in the quantum state, in some sense I tend to think of that as a universe. But for this talk, I'll imagine if different parts have different effective constants of physics, like different cosmological constants, different masses and charges and coupling constants, then I might say that those are separate, those are different parts of the multiverse. Those are made what you might call different universes. So there have been various books about this by various people that I know. There's this Leonard Susskind from Stanford who has a book on the cosmic landscape, string theory, and the illusion of intelligent design. How it can explain how the landscape can explain what otherwise might seem to be design. And then Alex Valenkin has a book, Many Worlds in One, The Search for Other Universes. He's one of the pioneers of inflation and of this eternal inflation. And then there's a recent book by Brian Greene that I basically have only read parts of in the airport when I missed a connection recently. But anyway, it seems, the parts I read seem quite good. George Ellis tells me there's one part about fake universes or simulated universes, maybe nonsense. But anyway, the other parts seem to be quite reasonable. So, now one quote about this occurred in the book that Bernard Carr edited. Bernard is here, although he doesn't have the beard anymore, but he edited the book. And Stephen Weinberg, in this book, wrote that just as Darwin and Wallace explained how the wonderful adaptations of living forms could arise without supernatural intervention, so the string landscape may explain how the constants of physics that we observe can take values suitable for life without being fine-tuned by a benevolent creator. I found this parallel well understood at a surprising place. And then Weinberg quotes Christoph Carlo Schoenberg, and I apologize, I don't know how to put umlauts on things, so I don't know in the New York Times, the 7th of July, where Schoenberg wrote, "Now, at the beginning of the 21st century, faced with scientific claims like neo-Darwinism and the multiverse hypothesis in cosmology, invented to avoid the overwhelming evidence for purpose and design found in modern science, the Catholic Church will again defend human nature by proclaiming that the immanent design evident in nature is real." So then Weinberg writes, well, it's nice to see work in cosmology get some of the attention given these days to evolution, but of course it's not religious preconceptions like these that can decide any issues in science. So here I wish to go on record as a Christian who respectfully differs from Cardinal Schoenberg's opinion. I feel a little nervous because I'm a Christian along with my fellow Catholics. I'm not in the Catholic tradition, but I understand, George Coyne yesterday was being critical of something that Cardinal Schoenberg wrote. So I think he's one voice for the Catholic Church, but he's not the only voice. So I don't wish to attack any particular group. It's just this was an outstanding spokesman, and I think he got this particular issue wrong. I did like his book. He had an excellent book that I agreed mostly with, but I think this issue, I think, is maybe a little bit misleading. Okay, let me give some of the reasons why multiverse hypotheses were invented. Contrary to what some people say, they weren't just invented often they were not invented purely for the reason of trying to explain the constants of physics. It's certainly not invented to try to do away with some theistic argument that God fine-tuned them. So, for example, there's Everett many worlds. This is in quantum mechanics, that the different possibilities given by quantum mechanics may all actually occur. And this was to circumvent the measurement problem of quantum mechanics. I mean, it formerly was thought that if the wave function collapsed when you made a measurement to one of the eigenstates, but Everett raised the possibility that maybe it never collapses. We just have the full state, and we have all these possibilities really occurring. Then in inflation, it was basically proposed that Alan Guth led off, and then Lindy and Blinken and many others have contributed a lot to. It was supposed to solve the flatness, homogeneity, isotropy, and magnetic monopole problems of cosmology. I mean, why is the universe so nearly flat? We saw the numbers in the excellent talks earlier about this. If you leave out the omega k, the omega k is very tiny, or omega matter plus omega lambda is 1.00, whatever it was, 1.02 plus or minus 0.02, or more precisely. It's very close to being flat. The universe, it looks like it's consistent with homogeneity. As George Ellis said, of course, we can't be absolutely sure. I mean, maybe there's inhomogeneity that we haven't found. It looks pretty much the same statistically in all directions. I mean, certainly not in this room, not in our solar system, not in our galaxy, not in our cluster of galaxies. But if you go on a scale bigger than about 10% of the linear size of the universe, then it looks pretty much the same in all directions. So crudely speaking, you could say if you divided the visible universe up into 10 ways this way, 10 this way, and 10 this way, you divide it up into 1,000 blocks, then each of the blocks looks pretty much the same. And then there were also problems in cosmology that magnetic monopoles might have been produced in too large a numbers, so inflation was produced to do that, but it's tended to lead, not necessarily, but it's tended to lead to these pictures of chaotic inflation or eternal inflation of the huge numbers of universes. Then the string landscape, they're trying to understand, I mean, this is a partial theory of gravity, it's by no means complete, but it does have a number of successes that it seems to be able to predict gravity, and it seems that it may have less divergences. I mean, it may be a finite theory, at least it seems to have less divergence than other quantum theories of gravities. And some people have found, maybe against their wishes, like Joel Polchinski, who I was rumored to have said that he would quit physics if a multiverse turned out to be right. But the string theory evidence sort of pushed it into saying that there at least seems to be a landscape, a number of different possibilities within string theory as to what the constants of physics could be. Now, I'm not an advocate of all possible multiverse theories. I think there could be good multiverse theories and bad ones, and there maybe could be good single universe theories and bad ones. Unfortunately, we don't have any good theory of either kind. But yet, we don't have a complete theory yet. So some multiverse theories do seem to be too artificial or contrived to be plausible, such as Davis-Lewis' modal realism idea that everything logically possible exists. Or Max Tegmark's original idea, he has modifications that maybe are more plausible. His original idea that all mathematical structures actually exist in more than a Platonic sense, that we are a mathematical structure and all of them exist. So some I'm not buying into all multiverse theories. I'm just saying that maybe some could be right. So other multiverse theories might arise naturally out of elegant laws of physics. So here's some ways that it might get it from physics. One natural way is just to have a universe so large that different highly varied conditions occur somewhere. I mean, even in the old days when we talked about Friedmann-Robinson-Walker universes, or approximately Friedmann-Robinson-Walker universes, if you had k equals -1, an open universe, unless you made topological identifications, it would go on forever. And if it went on forever, then you could say almost anything that could happen would happen somewhere, and in fact would happen infinitely often. Another way is from these Everett many worlds, that all the quantum possibilities are actually realized. Now these two possibilities do not necessarily give varying constants of physics. The Everett picture could just have different quantum conditions with the same constants of physics. So you might need something more if you want to get different constants of physics in the different parts. So inflation helps to get partway there. Inflation there is Alan Guth and Andre Lindy, who are probably the two leading, there's other people, of course, that have worked, it's arbitrary where you cut off the line. But anyway, though, if I had to name two that are the leading inflationists, I would name those two. So inflation is a very rapid expansion of the early universe that may make the universe very much larger than what we can observe of it. So the universe, we can see out, well, we could look back in time 14 billion years, so roughly speaking, we see 14 billion light years. Of course, what was there is now it might be roughly 50 billion light years across to this and 50 to there. So maybe the diameter is of order 100 billion light years if we count the present diameter of that. But inflation suggests that maybe the universe is exponentially much larger than that. You know, maybe 10 to the 10 to the something times larger than that. Now, if the constants of physics can differ across phase transitions, if there's perhaps more than one minimum of the potential, inflation tends to produce all such possibilities. So, well, here's a picture of the universe. Let's take that out. So, now let's go to the string landscape picture. Multiverse of strings. Here's some of the leaders of string theory and of ideas, some of these on the right, of ideas of string landscape. So recently it's been realized that string, or it's now sometimes called M theory because it includes other things like D-branes and so on besides strings. So sometimes they call it M theory. Nobody really knows what M means. So many things being mystery or mother of all theories, or maybe it came from matrix theory. So I don't know. And then I think Witten coined the name, and some people jest that it's just Witten's first initial upside down. But I don't know. Anyway, it's been realized that this theory apparently leads to a huge multiverse, and a common number that's thrown out, although it's very uncertain, is this 10 to the 500 or so different vacuum. So Michael Johnson here, whoops, sorry. Okay. He's done some counts of this. There's estimates of how many different Calabi-Yau structures, so on, that you can have, and you tend to get numbers of an order. Well, the exponent is highly uncertain, actually, but the exponent could be a few hundred, or maybe could be even in the thousands. So if this is true, you could have, each one may have different constants of physics. So there's a huge number of possible sets of the constants of physics that you could have. Now this would apparently be enough constants for what we see to occur somewhere in the universe. I mean, the cosmological constant we know seems to be about 10 to the minus 122. So maybe 1 out of 10 to the 122 of these universes would fit R by the cosmological constant. And then, of course, there are other constraints, and I know less about them. But let's be generous. I mean, I think the cosmological constant is the most severe one. The other ones are probably less. But there's probably a few, the exponent would probably be a few dozen higher. So let's be generous and say, very crudely, maybe 1 per 10 to the 200 vacuum or so. 10 to the 200, for those of you not math, means 1 followed by 200 zeros. 10 to the 500 is 1 followed by 500 zeros. Or Google is 1 followed by 100 zeros. So this is a Google times a Google times a Google times a Google times a Google, and this is just a Google times a Google. So it's much smaller. So the ratio would say that there's a Google times a Google times a Google, 10 to the 300 vacua, very, very crudely. I mean, this number could be smaller, could be much bigger. That would fit what we see. That what we observe of the constants maybe would be consistent with 10 to the 300 vacuum. Now, so if only one universe in 10 to the m, I mean the previous slide I had m of 200, could fit our observations, but if 10 to the n, and in the previous slide we had this crude guess that n is 500, if 10 to the n universe exists in the multiverse, then it might not be surprising that what we observe exists if this exponent, if the number that exists is bigger than what you need to fit our observations. Now we don't yet know whether n is bigger than m. We don't really know either one. I mean, I suspect m is probably between 120 and 200. I mean, well, that we're not quite sure. We're much less certain about the n. I mean, people say 500. I think it's more likely it's much bigger, but it's not ruled out. Maybe it's smaller. So if this is true, then what we could see could be explained with us having to be individually designed. We could say that if all of these different possibilities are realized, there would be somewhere where the constants would be appropriate for us, that they would allow our existence. Now, on the other hand, I'm not saying that anything that has big enough variety to allow our existence is a good theory. So, you raise the question, does the multiverse explanation always work? So, is it sufficient to explain what we see by a multiverse theory in which there are enough different conditions that ours necessarily occurs somewhere? So is it sufficient just to have a big universe, such that we know that big universe, we exist somewhere in it? Well, I would say no. I would say that the conditions that we observe should not be too rare out of all the conditions that are observed. We shouldn't be too improbable. If you selected, if you just made a random selection of what happens in these multiverses, we shouldn't be too unusual. We shouldn't be too rare. I mean, of course we're going to be somewhat rare. I mean, there's, even if you just say, 7 billion people on Earth, so that the chance that I'm me rather than one of those is like 1 chance in 7 billion. And if you include all the people that have ever lived, I mean, maybe it's 100 billion, maybe there's 1 chance in 100 billion that I have the characteristics of one of those humans. And if you allow many other planets somewhere else, there could be a huge number of actualized observers, and I'm only one out of that, so the probability that I'm me rather than one of those could be a very small number. But the idea is that it shouldn't be enormously small. There are theoretical possibilities that are far vaster than what might actually exist. So to put it another way, a theory making our observations too rare should not be considered a good theory. So this goes into what's called Bayesian reasoning after Reverend Bayes. So in rough terms, good theory should be both intrinsically plausible and fit observations. So intrinsic plausibility is quantified by the a priori probability of the theory. How probable would you say the theory is before you considered any evidence? And so in physics, scientists usually put higher plausibility to simpler theories, Occam's razor or parsimony. We tend to prefer simpler theories. We'll give them higher intrinsic plausibility. So if we use Bayesian analysis, we'd say have the higher a priori probability. But of course, you don't need that. You also need fit to observations. And this is quantified by the probability of the observation given the theory. If the theory were right, what's the probability that you get the observation? That's technically called, I think after Fisher, the likelihood, which is a very confusing word. It's not the usual word meaning of likelihood, but in statistics, the likelihood does not mean the probability of the theory. It means the probability of the observation if the theory were correct. So Bayes' formula gives the probability of a theory as being proportional to the product of the prior probability and the likelihood. And then you have to normalize it, so you have to divide by the sum of these products over all possible theories. But I'm not going to write down the formula. But basically, you need both. So the a priori probabilities of theories, that's the intrinsic probabilities before considering the observations. Now, as far as I can see, they're entirely subjective. There's no objective way to choose them. But generally, we humans do assign higher values for simpler theories. So this is Occam's razor or the law of parsimony of postulates. So we want to have the simplest postulates. We tend to think that before we look at the data that that's more likely. The data may force us not to take the simplest. It may force us to something more complicated. Now, we do tend for simpler theories, but of course even simplicity is somewhat subjective. I mean, computer scientists will talk about it, the length of the shortest input to produce some output. But of course this depends on your machine. Now they will often talk about producing infinite strings from infinite input, or very long input strings, and if the input strings are very long, it doesn't depend too much on the computer. But for the universe, we might hope that the theory is not extraordinarily complicated, so we might suppose that we have a relatively short input string. But then it's a question of what computers are running on. And David Deutsch noticed that simplicity depends on one's background knowledge, but our knowledge depends on the laws of physics themselves. I mean, what we know is dependent on the laws of physics. So in fact, although I'm a Platonist with regard to mathematics, I think the mathematics we use, the fact that we have integers, is because we have, in our physical world, objects that can be relatively separated. If we lived in a fluid universe, we might not use integers much. So the fact we find it very useful to use integers is a product of our world. I mean, the math exists whether or not, but the part we find useful depends on that. And so we tend to think integers are simple, but maybe if there was some other universe where everything was fluids, maybe some continuum would seem similar to those observed. So there's a lot of pitfalls of this. It's hard to make it precise. And even if we agreed on the order of simplicity, would there still be the question of how do you convert it to probabilities? I mean, I have a simplified way, just put them in order, take the simplest up, and then each one has a probability 2 to the minus n. So the simplest has a probability of a half, the next one a fourth, the next one an eighth, and so on. If there's an infinite number, that sums to 1. But that's totally ad hoc. I mean, it's simple, but it's ad hoc. Now the likelihood, or what's technically the likelihood, is the conditional probability of the observation given a particular theory. So if the theory were right, what would the probability be of the observation? So a theory that uniquely gives one's observation would have unit likelihood, but it may have very low prior probability. So if I wanted to have the maximum likelihood, I mean sometimes that's used in statistics, but if you don't couple it with priors, you get nonsense. So the maximum likelihood theory I can think of to explain my present observation is that only my present observation exists. None of you, actually you're all just part of my observation, you don't exist. Only mine exists. I think I have memories of doing things in the past, flying over and seeing Ellen, blah, blah, blah. But that's all a figment of my imagination too. Only my present observation, all that I'm aware of now, including my memories, exists. That would be an extreme solipsistic position. And if I had a theory for that predicted only that, it would, if I divide the probability among the unit probability only among that, I get unit probability. So that would be the maximum likelihood. But I think that theory is very complex. My observation is rather complex. It seems much simpler to explain the fact that I have the perception of seeing faces, most of whom I recognize from the previous times at this conference, quite a few of them I remember from previous conferences. Why do I explain all that? It seems to be simpler to assume that you exist. And you seem similar enough to me, I suspect that you have observations too. So I think this theory, even though it's maximum likelihood, I think the prior probability I assign is very low to this. And so I think when you take the product, I still think it's going to be low. Now the other extreme might be, well, let me give two extremes. I guess a priori, the theory I would say that would be the simplest would be the theory that nothing exists. Well, maybe I mean outside of pure logic, presumably, and logical relationship. Platonically, you might say they exist, so let's leave that aside, whether 1 plus 1 equals 2 even if. But let's suppose that no physically real thing or entity existed. That seems the simplest. But of course, if nothing like that exists, then my observation doesn't exist. So the probability of my observation given that theory is 0. So it's 0 likelihood, so I end up with 0 posterior probability for that. Now another one, which closest extreme, is a simple theory that predicts everything exists. And let's make it a little more precise and say that all possible observations exist with equal probability. And so there's a huge number of of observations, so the likelihood would be very low. In fact, I think it would be 0, because surely there's an infinite number of logically possible observations. And if you said each of these infinite number has equal probability, they'd all have 1 over infinity, and so it would be 0. So that's the way I would rule out Davis-Lewis's theory if you augmented it to say that all of the possibilities had equal measure. They all have equal probability. So those two don't work. Well, let's just give a toy example here. Let's suppose we have 3 theories, and let's suppose theory T1 has a prior probability very low, so 10 to the minus 7. But it gives unit probability for what we see. This would be like the solipsistic theory. I mean, the solipsistic theory, I would assign the prior probability much, much lower than that. I don't know, maybe 10 to the minus 50 or something. But anyway, just to put numbers I can print up here, let's say that this has a prior probability of 10 to the minus 7. We can give a probability 1 for what we see. So the likelihood of this theory is 1, the prior is that. Let T2 have a greater prior probability, only 10 to the minus 3, but it gives a probability of 1% for what we see. So maybe it predicts 100 possible observations that have equal probability, and we're one of them, so we have a probability of 0.01. Then a third one, T3, they have a prior probability of 0.999. So, well, and I could take off the 0.0, but let's just round it. So these 3 numbers are supposed to add up to 1 because they're rounded. And so you're almost, before you looked at the data, you'd say, well, we're almost certain of this theory. But it gives a probability of only 10 to the minus 7 for what we see. In other words, if this theory were right, what we see would have this small probability. And for the sake of argument, let's assume this exhausts the possibilities. So what you do is you multiply these together. You get 10 to the minus 7 there. You get 10 to the minus 5 there. You get 10 very close to 10 to the minus 7 there, so the sum is very close to 10 to the minus 5. You divide by 10 to the minus 5. You get T1 has a posterior probability of 0.01, T2 has posterior probability of 0.98, and T3 has that. So in other words, in this particular example, the one that has highest likelihood has low posterior probability. Also, the one that had highest a priori probability also has low likelihood. And the trade-off, the thing that gave a better compromise, in this particular case, gives the highest posterior probability. So you have this trade-off, and so that's basically what we have to think about. Okay, now suppose I'm a theist and I want to consider these, how might God have created the universe, and so, what priors might I put on things? Well, suppose we guess that God wants to create the simplest universe with beings like us in it. I don't know if that's right, it's just one guess. So now if the constants of physics we see are optimal, if they're the best for creating us, it might be simplest to God to choose them and them only. In other words, if what we see is really the best that's possible, then you might say, well, God just chose the best and he didn't bother about all these other things that aren't the best. So, but is that so? It's not clear to me that it is. The constants do seem very good, but it's not clear that they're optimal. So it might be simpler for God to choose a set of varying constants, a multiverse rather than a single universe. It might be a more elegant way to do it, in some sense with simpler. So you could ask this question, is the universe optimized for life? And I had a question I think I formally decided, is the previous slide I had from several years ago, but then this last year I read the nice book by Paco and Rubio, Questions of Truth, and it gave an example of this, that a theist would not be surprised that God had optimized the universe for life, not merely made life possible. So you might ask, is that true? Well, the trouble is, of course, it's hard to know what's optimized. And I tried writing a paper on this, asking the question, is the fraction of baryons in foreign living organisms maximized by the constants of physics, such as lambda? And anyway, let's see, so I was getting a hint of evidence against lambda being maximally tuned for this result, because the fraction of baryons that condense into galaxies would be higher if the cosmological constant were smaller. Basically, the cosmological constant puts as a repulsion. It tends to reduce things going in. Now, the observed value is really so small it has very little effect, but it has a tiny effect. And so if you reduced it, then there would be a tiny bit higher fraction of baryons in form galaxies. So now the question, of course, is the smaller value also optimize the fraction of baryons going into light? So if the fraction of baryons that went into galaxies, of the fraction that go into galaxies, the fraction that go into light is some subfraction of that. If that subfraction were constant, independent of lambda, then we could say that it would be better for the fraction of baryons going into life if the cosmological constant were smaller, meaning that the present value is not optimal. But that's uncertain. I posted this on the archive, and then Michael Salem sent me an email that this was not. It was not, even if this part is true. He agreed that this part was true, but he said it may not be the other. And Robert Mann wrote me a similar thing, and I had a number of email discussions with Nicholas Beale and with others, and particularly Martin Rees gave me the real expert opinion and told me that I was probably wrong, and it's by no means clear. Just because the fraction of baryons going into galaxies might be bigger if the cosmological constant, it doesn't necessarily mean that life might be bigger. There's just too many uncertainties there. So I changed the one-line title to about a 6-line title in the revised paper that's on the archive. So it does raise the question, is there something, could we make this testable? I was trying to make the hypothesis of optimal tuning scientifically testable, and it's a question of what can you? I mean, Nicholas Beale has suggested extremizing the expectation value of habitable Earth-like planets. So the question is, can we make that into a testable hypothesis and test it? And I don't think he or any of us are tied up in any particular thing, but it would be an interesting thing to see. I mean, if we really could find something about the constants that really were optimized, and that would say there were special values and we might believe that there's some principle or God or something that chose those particular values and perhaps didn't create a multiverse. On the other hand, if they're sort of, you know, in the range where life can exist, but not absolutely optimally to, then you might go to some other thing. So now the question arises: how do you assign probabilities to observations in a universe so large that there may be infinitely many observations of each kind? See, inflation tends to produce a universe that gets very big, and if you have conditions for eternal inflation, which does depend, as George Ellis was saying, on the constants and the potential, but a lot of reasonable potentials like m squared phi squared do give regimes where it's believed you get eternal inflation. That is, the universe can inflate to arbitrarily large size. And the trouble is that you may say, well, if we observe the cosmological constant, there may be an infinite number that observe the cosmological constant to be about 10 to the minus 122, but there may be an infinite that observe 10 to the minus 121, an infinite number 10 to the minus 120. And how do you take the ratios? Taking ratios of two infinities is very problematic. There can be ambiguities in how you do it. And this is known as the measure problem in cosmology. In my view, it's one of the most severe problems of theoretical cosmology today. How do you actually deal with these infinities? How do you actually make predictions for different values of the constants if you do have a multiverse? I pointed out a new twist in this thing, in that traditionally quantum mechanics has used Born's rule. Well, by Born's rule here I mean that probabilities are expectation values of projection operators. And I've shown that that does not work for the global quantum state of the universe in giving probabilities as quantum expectation values of projection. Oops, sorry, the plural should not be. Of projection operators. I have some papers on that, I won't go into that here. So even if the universe were finite, there still may be some ambiguities as how do we convert quantum mechanics into probabilities when we have the possibility of identical observers in different locations, and so identical I can't tell which location they are. But I won't get into that now. But so there's a whole lot of possible answers to this measure problem. Various people have proposed things, and I've proposed some. None of them look ideal. Even my own I have something about uneasy weighting in quantum cosmology, but it's got an ad hoc factor of 1 over 1 plus t squared. Other people have things that have congruences of GD6, and when the volume gets bigger than some amount, they cut them off. And other ones have a causal light code. You have one more line that goes up as far as it can. You take the light code, and you only count what's within that. So there's all sorts of procedures, but they all to me look a little bit ad hoc. This is a big unsolved problem. How do you do that? But using some of those measures, you can, and doing some very crude estimates as to what's required for life, it can suggest at least very crude values for some of the constants of physics. And in fact, I did some calculation where I combined some arguments of Brandon Carter and a later paper by Bernard Carr and Martin Rees on the constants of physics from stars, just the properties of stars. They had a power law relation between the strength of the electromagnetic coupling and the strength of the gravitational coupling. And then I combined that with renormalization group argument from particle physics, from the minimally supersymmetric particle model, to get a logarithmic relation. And then I got a single equation for throwing out let's see, Carr and Rees had a factor of 10 somewhere in their equations. And if I just dropped that, because that was kind of a fudge factor, then I got an equation that alpha log alpha is equal to minus pi over 100. And if you solve that, you get the electron charge, not even the logarithm, the electron charge within 92% of the observed value. So you can have an unattractive argument that gets even if you do it really, really crudely, that gets the electron charge right to within 8%. Other things you can get values of, but they usually differ because their numbers very far from unity in Planck units. For example, the cosmological constant's 122 orders of magnitude different. So you're not going to get that right to within a factor of 10. It's a question of getting the logarithm right. It's 120. And even the logarithm, that is how many digits it has, these arguments only get them right within maybe 16% or so. So anyway, you can have formulas for the electron charge, the electron mass, the proton mass, the cosmological constant, the human size, the planet size for for observers, planet size for observers living on it, star size, galaxy size, observable universe size, age of the universe. You can get formulas from these just from pure numbers. You just solve an equation like alpha log alpha equals minus pi over 100 and raise this to various powers, and you can get all these numbers, and the logarithms are right to that. So it seems somewhat suggestive that at least, well, I don't know, maybe that's not very suggestive, but you can do some quasi-predictions. They're not very precise, but they're sort of quasi-predictions you can get out from this. Okay, let me have another way of progressing the multiverses. I think this is influenced by what Mark Rees has said a lot, but I'm using my own examples. That you could say, well, you can start with one's present observation, and then you might go to solipsism, which not only believes that your present exists, but also your past. And then you might say, well, let's extend it more and believe that one's family exists. And then maybe you go a bit further and say, well, let's suppose one's nations exist, and maybe one's race, that's not necessarily a sequential order. And then you might say, well, we'll suppose that all humans on Earth, maybe they're all conscious. And then you might suppose, well, maybe other animals are also conscious. Here's our 3 dogs from home. Maybe extraterrestrials, that's not an actual photo of a real extraterrestrial, but just an illustration. You know, maybe they exist and have conscious perceptions. And you might suppose, well, maybe there's observers outside our past light code, that they're so far away they're not in causal contact with us. And then you might suppose, well, if we allow those, maybe there's observers in disconnected universes. Maybe there's universe splits into 2 parts and there might be ones in disconnected ones. Or there may be observers in different branches of the many world wave function. Or observers in universes with different constants of physics. Maybe even observers in entirely different universes. So we don't know where to stop. I mean, observations maybe take us up to, well, in some sense, really, I guess observation takes us here. But it's certainly very plausible to go along here. You can't prove it. I can't prove that any of you are conscious, but I think so. And we can't prove that. And this gets more uncertain. But it's a fuzzy where you're going to draw the line. Okay, let me now discuss some of the scientific objections to the multiverse. I think George Ellis will give much more of this. That one objection is that it's not observable or testable. But if you had a theory giving the distribution of different conditions, you can make statistical tests of our observations, whether they're likely or unlikely. Now, no such complete theory exists yet, so we don't really have a theory we can do a precise test of. But in principle, it's possible that you could do statistical tests and then see which works the best, dividing the priors and the likelihoods. Now, another objection is it's not a clear consequence of any theory. I mean, there's even debate within string theory. David Gross is a string theorist that's very skeptical about the string landscape. So it's not clear. But we need to calculate the consequences. We need to do more I'm not enough of an expert in string theory to do the calculations myself, but the people in string theory do to see, is this really a consequence of string theory? A psychological objection might be that, well, if we have all these different things, it makes things more complicated. But I think that's not really valid, because the whole can be simpler than the parts. The whole set of integers is simpler than most individual integers. I could put everything on the internet in principle could be a huge binary number, and that's one single number. And it's very complex, but it's contained within the whole set of integers. So I like to say that I think each of you is more complex than the entire universe. But unless you get too big-headed about this, I'll say an ant I believe is more complex than the entire universe. You might say, how is that possible? It's contained in it, but specifying the particular thing is what's complex. Like the big integer that has everything in the internet or everything in the Bible, just specifying what that integer is the complexity. Now, another objection might be that one seems insignificant if you're not unique. If there's copies of me out there, then okay, I'm not so unique. But it seems to me that one's purpose and significance need not depend on being unique. I mean, I'm here, God's called me to here to love others, to show mercy to others, and justice. I don't think that depends on whether or not there's a copy of me out there. The copy also has this requirement. So I think we can live with purpose even if there were copies of us out there. Now, a philosophical one that's almost the same as the psychological, you just say, well, it's extravagant to assume unfathomable numbers of observable universes. And again, the whole may be simpler than the part. And in particular, it may be easy for God to create. I mean, God, I believe, has infinite power, so he may prefer elegance over paucity. He may prefer elegance or simplicity of principle over small number of created things or small number of universes. Maybe the principles he might prefer to be simpler rather than the number of universes. Now also people say, well, it can be used to explain away anything because if you have the possibility wide enough that anything will occur somewhere, but that's what I've argued before. One needs to make that our observations are not too improbable out of all possible observations. I agree, any old wild multiverse theory is not going to be good. It's going to predict very low likelihood for ours. When you normalize the probability by making the probability for all possible observations add up to 1, that for typical or random multiverse theory, that's likely to give very small probability for us. So we need a special theory that makes our observations not too improbable. Then theological ones, this is, first it would be no more fine-tuning argument for God. But I think the loss of one argument does not mean the conclusion is necessarily false. I mean, we Christians didn't have to give up theism because Darwin came in and said, well, we evolved. I mean, there had been design arguments that depended on God separately designing the different species, and Darwin's undercut that, and that has upset a lot of people. But I don't think it needs to upset us. We can think that God created the whole process. Well, another point, you might say, well, if there's some simple multiverse, God has nothing left to design. I mean, this is like Stephen Hawking in his book, there's nothing left for the creator to do. But you could say that God created the entire multiverse, or the entire, whatever it is, you could still say God created it, and maybe he chose it to be that way. I guess another specifically Christian one might be if other civilizations out there somewhere have Christ, then you might say his death here on earth is not unique, as the Bible said. But it might be unique for our human civilization, and I think it's rather absurd to expect the Bible to. It's written for us. I don't think it's written to say what may be out there. If they're so far away that we're never going to have contact with them, it's not going to tell us. I mean, we're not told to go to evangelize them, but that may be because either they're too far for us to reach, or they have their own evangelists or something. So, actually, I think I'll do the other. This is from the top of that Mount Temple, from where I started my hike there, hiked up 1,700 meters. So, conclusion, multiverse, I believe, are serious ideas of present science, though they're certainly not yet proved. They could potentially explain fine-tuned concepts of physics, but they're not an automatic panacea for solving all problems. You can't just invoke multiverse, and now you've solved everything. And though multiverses should not be accepted uncritically, I mean, you really want to have a good theory that can predict the probabilities of observations. I would argue that scientists and theists have no more reason to oppose them than they had to oppose Darwinian evolution when it was first proposed. So my slogan is that God might indeed so love the multiverse.
First of all, Don, I'd like to thank you for the talk. I noticed the multiverse has infected your handout. I see duplicate copies of the conclusion on the back.
Yeah. Okay. Sorry. That's because look, it was a question whether you could read the writing here. So then I tried this one. I thought was best, but then this was like, so I had another one, but I didn't delete them out. So sorry. And then another one where. So that was sorry. That was I wasn't intending to show all of it, but I didn't realize it would be pretty.
I would like to question your idea of optimality. I mean, if you think in terms of, and you were talking in terms of theistic terms, what God would create. Given that God could create a universe of any size or multiple universes, I don't see any reason why God would make the constants, maybe there's a little more elegance to it, necessarily optimal for maximizing the number of observers, let's say, per galaxy. But I think there's another kind of optimality that would be important, and I've sent you the material on this, and that's for the optimized, the beauty, the elegance of the laws of nature, and optimized moral value that arises in the universe, particularly per conscious agent. And one of those, I think, one handle we can get on that is I think that giving us the resources to develop technology and science, actually, if you take my view of these things, contributes to our ability of a moral value, or we have the resources to better our lives. And so I think that the kind of optimality there would be constants or other features set so that we can have that technology. I do think there's a lot of fine tuning for technology and scientific discoverability, and you've seen some of the stuff I've sent you. So anyhow, I think that that's a more relevant kind of fine tuning or optimality than the other you talked about. I wonder what your response to that is.
Yeah, no, I appreciate that. I really appreciate a lot of email exchanges that Robert and I have had over the years since first meeting at one of these couple of meetings at Stanford, I think. So, yeah, I think I don't really know what ultimate value, God has, and I wrestle with the problem of evil and how does that fit into this, and so on and so on. And so I think it's useful to propose other things that God may well value. And it would be nice, I guess, if one wanted to test it scientifically, if one could at least come up with some particular predictions that you could test. I thought I was trying to do this with the cosmological constant, but it came out to be even that. We don't really know whether it's optimal or not. So I guess I would encourage it. I mean, in other words, well, in my view, God optimizes goodness, but I'm not quite sure what goodness is over the entire creation. I mean, I in some sense have this hypothesis like Leibniz that this is the best of all possible worlds. But I mean the whole thing. I don't mean necessarily each little piece is the best. But of course, what the best is, I don't know. And so it would be interesting to explore different possibilities, and then if you want to make it scientific, to try to put it in a form that could be testable. And if we really do find some criterion, some not too complicated criterion, by which we see the constants in our part of the universe really do optimize that, then I think that would be evidence for a single universe rather than a multiverse. So in principle, I think there is some testable things you could test between a single universe and as far as the constants of physics versus a multiverse if you found the right criterion. But of course, it's maybe difficult, and of course, if you find one criterion that doesn't work, that doesn't prove that there doesn't exist some other one that does work. So it's a difficult game, but I would encourage people to follow up on my very feeble and halting attempts to try to find something that you could test.
Thank you. Nicholas Beale.
Well, thank you very much for the plugette. The book is available from all good bookstores. I'd just like to say, first of all, this habitable Earth-like planets, which was sparked by the correspondence we had, it does seem to me, at any rate, that the hypothesis that the constants might, in some sense, maximize the expected number of habitable Earth-like planets in the universe. I don't know whether it's right or not, but it's something that would be relatively easy to test, whether you're at least at a local maximum, because you then only have to estimate the partial derivative of the expected number of habitable Earth-like planets with respect to each of the constants. And that is at least, I know that's a difficult problem, but it's a much less difficult problem than a less defined approach. And of course it gives you in principle, say, 8 or 10 partial derivatives. But the other observation I'd like to make, if I may, is we heard about the distinction between metacosmology and cosmology. And it seems to me that that's something to do with what you can observe and what you can't observe. And there are two reasons why you might not be able to observe something. It may be that you just can't observe it at the moment because you haven't got the tools, in which case you might say it's provisionally metacosmology, but it could be cosmology. Once you start getting to talking about other beings in other universes that are causally disconnected from you, then you're in a realm, it seems to me, of things that in principle you cannot observe. If something's causally disconnected, then by definition you can't observe it. And therefore whatever scientific theory might suggest about the possibility of things that exist that you could never, ever observe, we have to be very, very cautious about saying science shows they exist. That really is metacosmology. Oh, by the way, if anyone wants to collaborate on expected number of habitable Earth-like planets, please get in touch.
Yeah, okay, thank you, Nicholas. I'm doing a lot of stimulating email exchanges from you, and I guess this will be the first time we'll meet in person. Yeah. But yeah, so if that could be made really testable, of course, if it's total number, it's maybe a little hard to know because the universe is very big. So maybe you want some ratio or something, but I don't know. So it would be nice, yeah, if there could be something testable. I suppose as far as the meta thing, I'm impressed with the example. I think Martin used, if I remember, I used it in his talk the other night, that what's inside a black hole, you could say in principle we can't possibly observe. but we can test Einstein's theory elsewhere, outside, and then we can make the predictions. So I think I would be very I'm certainly not confident what happens at the Planck scale inside the black hole, or when the curvature gets to the Planck value. But I think I could be pretty confident of if I have a spherical black hole with no rotation, I think I could say pretty confidently what's happening if I go down to half the Schwarzschild radius inside the thing. So there may be so I think there are cases where I think science can make predictions that we can be very confident about, even about regions where in principle can't observe. Now I agree, it's much harder. I mean, in this thing is much more speculation, and we know much less. So I'm not saying it's at all quantitatively comparable, but it seems qualitatively I don't really see that there has to be a restriction in what science could say just because something is even in principle unobservable.
General Palazzo.
Yes, my point is the following. I appreciate what Weinberg says about the selection process, and I can understand that you will start with conditions that are rather general, and you will find some few that are real stable. I can understand this very well. But I don't understand why you speak of multiverse, because I think I can assume, perhaps I am wrong, that most of these alternative possibilities are simply dead ends, because they are not sufficiently stable. For instance, let us take simply the hydrogen, the most simple part of matter in our world. Okay, you have a huge amount of constants and elements that intervene here. They must be combined in very precise proportions. For instance, let's take the fact that we have the proton in the nucleus. This is a necessity, because the proton is, as far as I know, 1,840 times more massive than the electron. It is a necessity. This is a necessity for stability. Or you need necessarily a dipolar force, not a monopolar one, like the gravitational force. You need a force like the electromagnetic one, because you need a combinatorics in order to allow the different elements to be built. Otherwise, how you can build chemical elements? When you have a dipolar force, this allows you to have an exact proportion of electrons, protons, and so on. And moreover, when you speak, since the proton is the more massive particle, it must be a combined particles. This means a combined particle out of course. But most quark combinations are unstable. Only few are stable. And if you accept that you have an electromagnetic force, then they need to balance each other. I mean, the negative and the positive pole. But as you know, most of quark combinations don't give the right proportion. So the right electromagnetic value. So if this is true, and I don't speak now all other constants that intervene here, relativistic effects or whatever, the stack effect, and I mean, you may write a book like so on the hydrogen atom, and you will not exhaust the matter. So how can you assume so easily, or how physicists can assume so easily that other universes exist? This is something that I cannot understand simply. So what I am saying that you come out of several general conditions, but you are forced more and more to get on very few stable solutions. I will not say that our is the only universe, because this would be a sort of overstatement. But probably there are 2 possible universes, 3 possible universes, I don't know. Yeah, yes. But probably not 10 to 500. I mean, you know, when I follow you, I have the same sense how the last economical crisis in the US came out, because with such numbers.
We don't see any reason why a lot of the constants couldn't be sufficiently different that we don't allow life, and there still could be stable structures. Maybe they wouldn't be stable life structures, but you could have. So I guess I don't really agree with you that you couldn't change the ratio of the mass of the electron to the proton and not have stable atoms. So I don't buy.
My problem is not the value of the single constants, but how do you combine them? How do you combine all factors? I mean, there are hundreds of different factors that you combine only for the hydrogen. This is my point. Not for the single values. You can do the game with the single values as you like, but not with your combination. You need to put all that.
Well, I don't understand. I mean, if you have all the values, if you could just change one, I mean, leave the rest the same. Then that's changing the whole set. I mean, if you regard the set as a whole, if you change any element in the set, you change the set. So if you click change.
No, you need to traverse. You need to traverse this reasoning. Sorry. Because the problem is not if you change one, you will change the rest. The problem is how you converge on a value that is the exact value needed for such a physical problem. That is how I can pick out the values of all these constants in order to get something that is really physical. So I will traverse the reasoning. Because the other way around, I don't think that we will arrive to some significant results.
Agree, Bob, we're going.
Yeah. I don't know, as far as I see, the equations that we presently have, admittedly they're not the final, the present ones seem to allow variation in the constants, and you can still have solutions. So I don't see this restriction as far as solving the equations. There's a range. I mean, of course, it's not a point. It's not even a point that allows life. There's some range that allows life, or maybe some other range over here. But I don't see that just requiring that the equations of physics have solutions, or even have stable solutions, really puts the restriction on it that you seem to have in mind.
Well, thank you. I think we have to be here. I think it's now lunchtime.